We'll now use a water circuit model to measure the pressure difference across two resistors in parallel. We'll show that the pressure difference is the same across both resistors that are connected in parallel. Just as a battery pushes charged particles through an electrical circuit, our water pump pushes water through our water circuit. In this circuit, we have two resistors connected in parallel. You'll notice that the resistors are not the same. One of the resistors is longer, and you know that resistance is proportional to length, so this resistor has a larger resistance. In this demonstration, we're using water pressure as an analogy to electric potential. So we'll measure water pressure using these vertical tubes. The height of the water in the tube is proportional to the pressure. Let's measure the water pressure, again, our analogy for electric potential. The height of the water before it enters the long resistor is 51 centimeters. The height of the water before it enters the short resistor is 50 centimeters. Now let's place the vertical tubes after the resistors and see how the pressure changes. Now we have the tubes positioned after the resistors. Let's measure the height of the water in each tube. 11 centimeters after the short resistor. Also 11 centimeters after the long resistor. So if you remember from before, the pressures before were 50 and 51. So the difference in pressure across each resistor is 40 for one and 39 for the other, which is effectively equal because we have experimental error whenever we do a measurement. The electric potential of charged particles before they enter a resistor is higher than the electric potential after they go through the resistor. So there's a drop in electric potential as charged particles travel through a resistor. And we see that with our water analogy because the pressure or the height of the water dropped before and after the resistor. This difference in electric potential, often called voltage, is the same across resistors in parallel. So we've seen that the pressure difference across resistors in parallel is the same. Now let's measure the pressure difference across the pump. This vertical tube here will give us the pressure in the water as it leaves the pump, 54 centimeters. This vertical tube will give us the pressure in the water as it enters the pump, 7 centimeters. So the difference is 47 centimeters across the pump. If you remember, we had a difference of 40 centimeters across the resistors. As I've said before, we have additional resistances in the circuit due to these junctions and even these clear tubes, so we're not going to get an exactly equal value. What we can see is that the water gains pressure after it goes through the pump, and then it drops in pressure after it goes through the resistors. So if you were to follow one complete loop of the circuit, the gains in pressure would be equal to the losses, so that the total change in pressure would be 0. This is the same as an electrical circuit. You have charged particles moving through a loop. When they go across the battery, from the negative to the positive terminal, they gain electric potential, and then their electric potential drops as they go through the resistors. And when they go through one complete loop, the total change in electric potential is 0. That's consistent with Kirchhoff's loop rule. Let's examine current through the parallel configuration. I have a pump, a clear tube, and then 2 resistors in parallel. Let's see how much water flows out of each resistor in 10 seconds. So out of the long resistor, we have 180 milliliters. And out of the short resistor, we have 250 milliliters. Let's connect these and see how much water flows out of the junction in 10 seconds. I've connected the 2 resistors now so that the water will come out of one junction. Let's see how much water comes out in 10 seconds. Okay, that's 425 milliliters. So we had 180 milliliters of water come out of the long resistor and 250 milliliters come out of the short resistor. That's a total of 430 milliliters. When I connected them, we measured 425 milliliters come out of the junction. So what we can see is that the water entering the junction didn't disappear and it didn't come out of nowhere. The same amount of water that went into the junction left the junction. So we can account for all the water entering the junction. It all leaves the junction. Now you're going to use a simulation to answer some questions about circuit behavior.